Welcome back to Kine 3030 Online. Today we are going to do one of what I think is the most important ideas that you will get out of this course, and that is the idea of equilibrium at the joint level. Last class we talked about equilibrium, the idea that the sum of the forces in the x and the y direction equals 0, and the sum of the torques around point equal 0 around an axis. And we looked at it from the perspective of a whole body. Today we're going to look at it from the perspective of, can we use that to figure out what's happening at a joint? And which ultimately tells us which muscle group is active and how active it is. So, to review, as we talked about in the last class, a static equilibrium is that state characterized by balanced forces and torques, meaning the accelerations are 0. It occurs when the accelerations are 0. Okay? And that's the accelerations in all directions, x, y, and angular. And because of that, if you put a 0 into Newton's second law, you're going to get the sum of the forces equals 0. 3 conditions, again, that you need to have are the sum of the forces in the x equals 0, the sum of the forces in the y equals 0, and the sum of the torques around some point equal 0. And just as an example, let's think about using this resistance band. And if I had a resistance band, oops, that wouldn't be how I would use it. It doesn't work very well with not running shoes. So you're using a resistance band with a client, and they're recovering from a biceps injury. They're doing some biceps curls, and you want to know how the resistance band will affect the ground reaction force, assuming the mass of the band is negligible. So I have 2 free body diagrams here. I have the free body diagram on the left, which is them in the posture without the band intact, and the one on the right is with the band on intact. And you see you have the weight of the whole body. And again, we're assuming that the weight of this is negligible. And we have the ground reaction forces in the x and the y direction. And of course, because it's a free body diagram, we have our reference frame up at the top. So we do, in both cases, we'll look at the sum of the forces in the x direction, of which the only force in the x direction is the ground reaction force in the x direction, which means the ground reaction force in the x direction has to equal 0 in this particular case. And we have the sum of forces in the y direction, which of course is the ground reaction force, which is acting in a positive direction of the y component, and the weight of the person, so, which is negative. So the ground reaction force underneath them in the y direction is going to equal to their weight. That makes fairly sense, and you'll note it's the same for both. In other words, this didn't make a difference. Why didn't this make a difference? Because the force of this band is within the system. So as I'm pulling up here, I have a force going down, which is created by the band on my hands, and I have a force coming up, an equal and opposite force. I mean, it's the same force coming up, and it is equal and opposite. So same magnitude, opposite direction. It's going to cancel. It's inside. That's the reason why all of our muscle forces and our joint forces in our whole body, if we're looking at the whole body, they'll cancel each other out. But so that's where we are for the whole body. So in other words, really doing a whole body version of this isn't really useful, because ultimately what the client wants to know, what you want to know on behalf of your client, is how much activity they have to do in, let's say, the load on their biceps. Or you could choose another joint, but if biceps is what's of interest to them. So you need to look at what's happening at the joint. So the objective today is to look at the understanding of the statics to problems at the joint level, and to investigate application of static equilibrium in order to understand statics at the joint level. So we can use it to try and predict what's happened, which muscle group is active at a joint. So in the whole body, there's, again, no forces or torques acting on the body as a whole. We're stationary, or we're moving at a constant velocity in a constant posture. And at the joint level, those same equations apply. The very same equations apply. The difference is that the system of interest now is a body segment, because we need to chop through a joint. We have to chop through the joint of interest in order to get a body segment that we can then look at the forces on the segment, of which the forces on the end of the segment, in the case of elbow for the forearm, it would be the proximal end of the segment, are going to be what's happening in this joint. So again, if you look here, if we want to know what's happening in the elbow, if we want to know for example, the joint reaction forces or the bone-on-bone forces, there's two slightly different things, but the bone-on-bone forces between the humerus and the ulna, for example, which is the elbow joint. We want to know what the biceps muscle is doing. We have to cut. Those are all things that happen at the elbow. So we're going to cut through the elbow. And we are now going to have this body segment. In this case, we are left with the forearm and hand, really. And you can see what we've done is we've replaced the rest of the body as defined, as shown by the humerus, with forces. So that's what we do. When we remove the rest of the body, we replace the rest of the body with forces. We are going to have contact forces between the two bones. That's your Fx and Fy, F vertical, X, F horizontal. And we're going to have a force created at the muscle. And you can see it's in line with the muscle. We've talked about muscle forces before. Muscle forces are in line with the line of action of the muscle. So you can see there's a force pulling, because muscles pull, on the forearm in line with the biceps. So we've cut out the biceps and we've replaced it with a force. If we were now looking back at our using these again, we would cut through the forearm or through the elbow, because we want to know what's going on in the biceps. If we want to know what's going on in the biceps, that's what we've talked about. That is our joint of interest. We're going to cut through there. And what are we left with after we cut through there? Well, we have a forearm now, which has the force of the elastic band on starting at our hand. You can see that. So now there's no other side to the elastic band, so we can actually look at what the elastic band is doing to our body, particularly the upper limb. So we have the force of the band. We have the weight, but now it's the weight of just the body segment. The body segment of interest is the forearm and hand, so it's the weight of the forearm and hand, and the weight of the forearm and hand only. Only, okay? It's not, there's no other weight, there's not the weight of the whole body in there anymore. It's just the weight of the forearm and hand because we are only looking at that body segment. And then you can see there's the green there, which is the force of the biceps. And then we have the two small ones that are acting right at the joint itself. So our two joint forces. None of the other forces matter anymore. We only are looking at those ones in order to figure out what is happening at the elbow. I will say that you can do it either way. You can look at either the forearm and hand as one segment and look at all the forces associated there. Or you can look at all of the rest of the body except the forearm and hand. So think of what that would involve, because the bone-on-bone forces, the joint forces that we're looking at here, there would be equal and opposite joint forces on the other side of on the humerus side of the elbow, and you can see those shown here. There will be a biceps force that would be coming from the origin of the biceps instead of the insertion of the biceps, and you can see that force there. You now have a weight of a whole body, but it is not the weight of the whole body. It is the weight of the body minus the weight of the forearm and hand, because that forearm and hand are being looked at separately. And we have the ground reaction forces and the elastic band force only where it applies from the foot, not from where it applies at the hand. So you can actually use either one of those free body diagrams to do your analysis, but we typically use the one that is the distal portion, the distal segment. Why? Because A, we know more about single segments, and B, there's a lot more forces that you have to deal with in the whole body one, because minus the forearm and hand, because you have those extra ground reaction forces that you need to know. So let's do a fairly simple problem, a typical problem of what this means in terms of actually calculating a muscle force. So if we have the quadriceps tendon, and it's going to attach to the tibia at 30 degrees, and that is going to attach 4 centimeters from the joint center at the knee. We add an 80 Newton weight attached to the lower leg, 28 centimeters distal to the knee joint, and we want to know how much force is required of the quadriceps to hold that in position. We also want to know the magnitude and direction of the reaction force at the knee itself, exerted by the femur onto the tibia. We are, for the purposes of this problem, going to neglect the weight of the actual body segment, the lower leg, the calf. That isn't always the case, but for the purposes here, for your sort of first time, we're going to just go with neglecting that body segment weight. So here's a picture of what we're talking about. We're in a situation where the weight is being held up on they'd be sitting. If we were still in the classroom, I would jump onto one of the desks and reproduce this. But you can see that calf is being basically held horizontally, and you can see that the weight is on the calf 28 centimeters out. I've created a free body diagram of the situation down below where you can see the 80 Newton weight, 28 centimeters from the joint center. We have the two forces at the joint center. I've broken them into the two components. Which direction those two components are shown at is what you might think it's going to be. It may not end up being in those directions. You draw it and you put the sign of the forces based on your reference frame. And then we see if it turns out to be positive or negative, because that will tell us whether they're acting in the direction you've drawn them or in another direction. So, step 1, create that free body diagram. Step 2, we can do torques around the knee. Typically, we often do the torque first. Why would we do the torque first? Because we really want to know in many cases, unless you're working with, artificial joints, often what you're looking for is how much muscle activity you have and how much force there is in the muscle. The other reason is because if I take torques around the joint center, I have a situation where where the moment arm for the force in the X direction and the force in the Y direction that are at the joint itself, they have a zero moment arm. So there's no torque being created by those two forces, those two force components. There is no torque being created because there's zero moment arm. The only thing that creates a torque in this static situation around the knee is the muscle, quadriceps muscle itself, and the weight of the hanging from their ankle. So the sum of the torques equals 0. This is in static equilibrium, meaning 0 accelerations. Basically, it's a static situation, which is what we sort of look at here. And you have a counterclockwise, I'm considering positive. So you can see, as I've drawn my free body diagram, the torque being created by the quadriceps is going to be positive, and that's going to be 4 centimeters, times the actual force of the muscle, times that sine 30 degrees, because that talks about the component that is acting perpendicular to the bone, minus the 80 newtons times the moment arm for that, which is 0.28 meters. If you solve for that, because that all equals 0, the only unknown there is the force of the muscle. So the force of the muscle is going to equal that 80 times 0.28 divided by 0.04 times sine 30, or 1,120 newtons. I'm hoping you're seeing here, it's important to recognize that the muscle force in this situation is much greater than the actual load that is carrying. And that's even ignoring the weight of the calf and foot. We're only looking at that 80 Newton weight, and yet in order to hold the 80 Newton weight in that posture, the muscles have to create over 1,000 newtons of force. That's a really important thing to recognize about how muscle works. Oops, sorry. So we can also look at the forces in the X direction. there is the actual force of the joint force that is a component of the joint force X, which is acting in the positive direction, and in the negative direction, so minus, is the component of the muscle force that is acting towards the joint. So FJX minus 1120 newtons times cos 30, because that'll be the component that's along there, means that joint force in the X direction equals 970 newtons. In the Y direction, we have the joint force in the Y direction. As I've drawn it, it is pointing up, so I'm going to put a positive there. We have the muscle force component that is in the Y direction, which is the 1120 newtons times sine 30, because that's the part that's going up and that's acting in the Y direction. And that's also in the positive direction. And then minus the 80 newtons. If you solve for that, the only thing there that you don't know is the joint force in the Y direction. You're going to get negative 480 newtons. What does that negative mean? That negative just means that the force is actually acting down at the joint. That the force of the femur acting on the tibia is acting down on the joint. I drew it up, so it's either pointing up and it's negative, or it's pointing down and it's positive. If I had drawn it down in the first place and put it into my equation that way, which would have meant a negative, it would have, everything would have come out and it would have ended up as positive. So you don't have to change it. You don't have to change how you drew it. You just have to recognize what that negative sign means. So that was all well and good, but what happens if there's more than one muscle acting? If there's more than one muscle acting, and what other muscles could there be? There could be other agonist muscles, or there could be antagonist muscles. Or there could even be ligaments that are stretched that are not acting right at the center of the joint, so they might actually create some torque also. So we could have co-contraction of a number of muscles. How do I deal with that? Well, I'm going to say that there's a number of approaches to dealing with that. There's quite a few approaches to dealing with that. There's two that we're going to talk about at this level because, to know better, more approaches, which can go from some modeling approaches, EMG, the use of EMG on all the muscles to see how much activity there is of all the muscles, or there's even approaches that are invasive, that involve actually putting force transducers on the tendon. But at this level, we're going to talk about two approaches. One is what's called single equivalent muscle. And that says that all of the torque that is being created at the joint is being created by one muscle. Okay? So, in the if I'm doing a flexor activity, a biceps curl, for example, I'm doing a biceps curl, I'm saying everything that is creating flexion, creating that flexor torque is being created by the biceps. And it's pretty easy to do on some of the main joints like the biceps, triceps, and the everything that goes through the Achilles tendon, for example. I know that's triceps surae, I know that's 3 muscles, but that all goes through the single tendon. So we can choose a muscle that takes the whole torque, creates the whole torque. So in the case of a biceps curl, it means that biceps is the only one that is on something like the brachioradialis, which also creates a flexor torque, is not on. It's not taking some of it. The triceps, which of course would be the antagonist muscle, is not on. It's all being created just by the biceps. And that's what we call single equivalent muscle. Approach. Another approach we have is to say, you know what? We know there's multiple muscles that are on. We know that you're doing this activity, and while you're doing this activity, you happen to co-contract both your biceps and triceps at the same time, and you turned on your brachioradialis to break the tie. So there are a number of muscles creating torque. So we could just add up all of the muscles creating torque and come up with a net torque. And we can create a net torque even without assigning it to any muscles. If we can either create a net torque from the external forces that are acting on the systems, or if we happen to know what all the different muscles were doing, we could add them all up and subtract them. So all the ones that are acting in what we consider a positive direction would be acting. We would add. All that would be acting in what we would consider a negative direction, we would subtract. And we'd add them all up, and we'd have a net torque. The thing about, and net torque is something we do very commonly. The only thing that I have to say about the net torque situation is that the forces that you get at the bone now no longer include, if you look at the question before, you'll see that a fair amount of that force that's happening at the between the two bones comes from the muscle itself. And so if we look at it from a torque perspective, we're going to have what we call net reaction forces at the joint, but it won't be the complete bone-on-bone force. So we recognize that the individual muscle torque is the product of a muscle tension and a muscle moment arm, and that the net joint torque is the sum of all the individual muscle torques. And the net joint torque will always be in the direction of the agonist muscle. So whichever we come up with as our net joint torque, that is the direction of the agonist muscle at that instant in time. And that is really the definition of the agonist muscle. So that's what it is. Why would we use this approach? Well, the big advantage is that you don't need to know which muscle group ahead of time is actually active. You don't need to know. It's going to tell you which is the agonist muscle. You also don't need to know information on a very specific muscle. So let's say I'm doing some activity and I just don't happen to know which muscle group is the agonist, whether it's the flexors or the extensors or the abductors or adductors. I don't have to know that ahead of time. It will come out as to which one is the agonist muscle. And being that, so if I'm doing a biceps curl, and let's say we know that it turns out that it is a flexor activity, and I might say, okay, the biceps is the agonist muscle and it's the only one on, but I need to know, if I'm going to use that single approach, muscle approach, I still need to know the moment arm of that muscle, right? So there's a lot of information that I don't need to know. I don't need to know how many muscles are active. I don't need to know what other agonist muscles are active and what other antagonist muscles are active. I don't need to know the division between the different muscles as to, what's taking what percentage of the load. And I don't need to know the moment arms of each of the active muscles. So by using this approach, you can see that there's a lot of, you still find out which muscle group is active, and you're getting a torque, so it's comparable to strength, because strength is a torque. You can compare it directly to strength, so you can figure out what percent MVC you're actually working at, all those kinds of things. And you don't need to know this other information about the specific muscles. The disadvantage is that it doesn't actually give you a force in the muscle. So if what you're interested in is, you're looking at a specific tendon injury, and you want to know how much force is being pulled in that tendon by the people who are getting these injuries, you wouldn't get that. You need to do that next step to figure out how much force is actually in the muscle, to figure out how much force would be in the tendon. You also, as I said, because it doesn't include muscle forces, the forces you get at the joint, the reaction forces you get at the joint, are not the full picture. They do not include the effect of the muscle force, so they underestimate your bone-on-bone forces at the joint. So we're going to redo that question we just did, only this time we're going to just do it as a net torque approach, and we're going to ask, is it a flexor or an extensor torque? So we're going into it without knowing which muscle happens to be active. I know in this particular activity, all of you would know that this would be a quadriceps activity, but let's say you didn't. And you don't need to know ahead of time. You don't need to know what that moment arm of the quadriceps tendon is. You don't need to know, or its location and angle of pull. So instead of, here's your free body diagram, and this is that again, same situation we just did, only now I don't have a muscle force on them. Now, you do not understand this. You do not put both a muscle force and a torque at the same time on the same free body diagram. It's either just a joint torque, basically saying that the torque being created by the muscle is all just one torque, and you draw a torque around your joint. Or you know which muscle is active and you draw the muscle from the line of pull from where it attaches, at the angle of attachment, etc. You draw that force in. You don't do both. You do one or the other. You either do the torque approach or you do the single equivalent muscle approach. This one is the torque approach, and you can see at the knee, I still have my two joint forces, only this time they would not be the same. They would not be as much, and you'll see that. And I have, instead of a quadriceps tendon force being created by the quadriceps, I just show a joint torque. And I want you to really make sure you understand how I've drawn it, that represents actually, as I've drawn it, it's an extensor torque. Okay, as I've drawn it, it's an extensor torque. As I've drawn it, it's going to try and rotate, if this was my foot, and this is my knee, it's going to try and rotate it up, which would be a knee extensor. Knee extensor just happens to be the quads. So I now do the sum of torques around my knee joint, just as I did in the other one. which is the torque at the knee minus the 80 times 0.28, the torque created by the weight at my ankle. And I now can solve for the torque at my knee, which is 22.4 Newton meters. So the torque being created by my quads, or this person's quads at this point in time, is 22.4 Newton meters. And if you ever had them do a max, you could compare that 22.4 Newton meters to the torque of their max to get a percent MVC, for example. So it's very useful. It's also positive. And what does that mean? Is it an extensor torque or a flexor torque, and how do we know? As I've drawn it, and as I put it into my equation, I drew it counterclockwise, which happens to be what I consider positive if you look at my reference frame. And it also, I would always have a pencil nearby. This is it, when you're writing any of these tests or anything, you want to have something like a pencil, and you hold on to it, or a phone, hold on to it at the joint end, and then you push down on it and see which direction it goes. If you push up on it, you see which direction it goes. As I've drawn it, it would be pulling up like that, which would mean, again, an extensor torque. You can see as I've drawn it, which is how I put it into my equation, it's the quads that would be positive. If I had ended up with a negative value here, I again would not change the direction of my arrow. I would keep it as a negative value, but I would say, because it's negative, it means at this instant in time, the hamstrings or my knee flexors are active. That isn't the case in this situation, but if it had been a negative, that's what it would mean. So I'm going to leave you with this problem, and we're going to say that our client who we're doing the biceps work with is a little concerned about what's happening with their shoulder problem, and you want to figure out which muscle group is active at the shoulder, and determine which muscle group is active and figure out how much. And do a proper free body diagram. So I'm going to leave that with you so that you can figure out what's happening at the shoulder at this instant in time. And again, we're talking static here. We're not talking highly dynamic movements, because then it wouldn't be an equilibrium. But in a static situation, what's happening at the shoulder there. And we will see you next lecture.